Right now, at this precise second, a machine launched before many of the people listening to this were even born is racing through the absolute darkness. It is drifting 25 billion miles from the soil where it was built, farther from home than any object humanity has ever touched. It is a tiny speck of metal, an assembly of gold-plated copper and aluminum, drifting against a backdrop of distant stars that look cold, unmoving, and utterly indifferent to its existence. This is Voyager 1. But here is a fact that should terrify you, a fact that puts our entire existence into a humbling, almost crushing perspective. If this probe were heading toward our nearest neighboring star, which it is not, it would take 73,000 years to arrive. We are about to leave the safety of our home and journey beyond the edge of everything we know. We are going to explore ships that ride the shockwaves of nuclear bombs, meet civilizations that harvest the energy of entire galaxies, and stare into the face of a time when the universe itself will die. What we are about to uncover will change how you see our place in the cosmos, for the story of humanity's future is not just about rockets or fuel, but about the fundamental struggle of life against the encroaching dark. To understand where we are going, we must first understand where we are. Picture yourself standing at the shore of an ocean that stretches beyond every horizon you can imagine, an ocean so vast that our entire history is but a single grain of wet sand on its beach. You might think our solar system ends at Pluto, the lonely dwarf planet of ice and rock, or perhaps the Kuiper Belt, where billions of icy rocks dance in the dark like a swarm of frozen fireflies. But you would be wrong. The solar system is much, much larger than that. Way beyond that distant ice ball, beyond the scattered debris of the planet-forming era, there is a region called the heliopause. This is the true border. This is where our sun's influence finally dies. This invisible border sits about 11 billion miles from home, a distance so incomprehensible that light, traveling at 186,000 miles per second, a speed that could wrap around the Earth 7 times in a heartbeat, takes 16 hours just to reach it. If you stood on the deck of a ship at the heliopause and shone a flashlight back toward Earth, you would have to wait 16 hours for anyone to see it, and another 16 hours to get a reply. If you drove a car at highway speeds, without sleeping, without refueling, the trip to this border would take you 12 million years. You would see civilizations rise and fall, continents drift and crash into each other, and ice ages come and go, all while you were still just backing out of the driveway in cosmic terms. Think of our solar system like a giant soap bubble floating in the dark. The sun is not just a light bulb, it is a breathing, violent engine of fusion. It blows this bubble with the solar wind, a relentless stream of charged particles, protons and electrons racing outward at 1,000,000 miles per hour. For billions of miles, this wind pushes against the emptiness, creating a shield. It inflates a magnetic bubble called the heliosphere, a protective cocoon that wraps around all the planets, shielding us from the worst of the galaxy's radiation. But eventually, even the sun's mighty breath grows weak. The pressure drops, the wind falters. At the heliopause, our solar bubble crashes into the fierce winds of interstellar space. This is not a quiet line in the sand, it is a turbulent, chaotic frontier. Here, alien particles from exploded stars, the radioactive shrapnel of supernovas that went off millions of years ago, slam into our cosmic neighborhood like waves crashing against a seawall. The temperature drops to nearly absolute zero. The magnetic fields twist into chaotic ribbons, snapping and reconnecting in violent bursts of energy. You have left the only sanctuary humanity has ever known. You are now in the interstellar medium, the space between the stars.
Voyager 1 crossed this boundary in August 2012, becoming the first human-made object to enter true interstellar space. Its radio signals, transmitted by a transmitter with the power of a refrigerator light bulb, now take over 21 hours to reach Earth. They whisper back data from a realm so foreign that our best scientists are still decoding the static. The data tells us that the space out there is denser than we thought, filled with a fuzz of low-frequency plasma waves. It tells us that the magnetic field lines of the galaxy are smoother than expected, but cold, unimaginably cold. But here is what should make your head spin. This edge, this boundary that took us 35 years to reach with our fastest machine, moving at 38,000 miles per hour, represents less than 1/10,000th of the distance to our nearest neighbor star. Imagine taking a single step. That is Voyager's journey. The journey to the next star is equivalent to walking around the Earth 2.5 million times. If the distance to the Sun was 1 inch, the distance to the next star would be 4 miles. The scale is broken. Our brains, evolved to hunt on the savannas and track animals over a few miles, simply cannot process these numbers. We use words like astronomical or huge, but they are meaningless placeholders for a reality that is too big to fit inside a human skull. These probes, Voyager 1 and Voyager 2, are our medieval ships sailing for continents they will never reach. They are time capsules sealed against the vacuum. They carry a golden record, a 12-inch gold-plated copper disc, a message in a bottle thrown into the cosmic ocean. It contains the sounds of whales singing in the deep Pacific, the cry of a newborn baby, the sound of a kiss, the wind, the rain, and the thunder. It carries greetings in 55 languages, from Akkadian, spoken in Sumeria 6,000 years ago, to Wu, a modern Chinese dialect. It carries the music of Earth, from the intricate counterpoint of Bach to the rock and roll of Chuck Berry and the haunting flutes of the Solomon Islands. It also contains images encoded in analog grooves, pictures of humans eating, drinking, running, and building, diagrams of our DNA, a map of our location using pulsars, rapidly spinning neutron stars as cosmic lighthouses to triangulate the position of our tiny yellow sun. In 300 million years, long before Earth has been swallowed by the sun as it expands into a red giant, long before humanity has either ascended to the stars or vanished into dust, this record may be the only proof that we ever existed. It will be a silent monument to a species that once looked up and dared to reach out, drifting through the dark long after the hands that built it have turned to stone. By 2025, Voyager will fall silent forever. Its nuclear heart, a generator powered by the radioactive decay of plutonium-238, is dying. The heat is fading. The voltage is dropping. NASA engineers have already begun shutting down heaters and scientific instruments one by one to save power, like closing the rooms of a great house as winter approaches. Soon the transmitter will fail. The probe will become a ghost ship, a dead hulk of metal sailing the darkness for eternity. It will orbit the center of the Milky Way once every 225 million years, a silent traveler on an endless loop. But Voyager taught us the most terrifying lesson of all, a lesson that challenges every sci-fi movie you have ever seen. It taught us that space is not just empty, it is violently, aggressively empty. Between us and the next star lies a darkness so complete it makes the deepest ocean trench look like high noon. To understand this emptiness, we have to play a game of scale. If we scaled the solar system down so that Earth was the size of a marble, the Sun would be a beach ball located about 150 yards away. Jupiter would be a golf ball a few blocks down the road. But the nearest star? The nearest star would be another beach ball located 1,400 miles away. Imagine placing a marble in New York City and expecting to hit another marble in Denver with a perfect throw. That is the challenge of interstellar travel. It's not just about aiming, it's about traversing a void that defies description. The emptiness goes deeper than just distance. It's a physical quality of the environment. In the best vacuum chambers on Earth, the most expensive scientific equipment we have, we can pump out almost all the air. But even in our best artificial vacuums, we still have millions of atoms per cubic centimeter. In the atmosphere of Earth at sea level, there are billions of trillions of atoms in a thimble of air. But in interstellar space, there is less than 1 atom per cubic centimeter.
This is a vacuum so perfect, it is terrifying. It sucks the heat out of anything. If you were to step out of a spacecraft without a suit, the moisture on your tongue would boil instantly due to the lack of pressure, while the side of your body facing away from the sun would freeze solid. And it is toxic. Without our sun's magnetic field to sweep them away, we are exposed to cosmic rays, high-energy protons, and atomic nuclei stripping through the galaxy at nearly the speed of light. These are shrapnel from dying stars and hungry black holes. A single cosmic ray can carry the kinetic energy of a baseball thrown at 60 miles per hour, condensed into a subatomic point. These are invisible bullets. They shred DNA. They smash into the silicon of computer chips and flip the bits, causing errors. They fry electronics. To travel the void is to walk through a minefield in the dark. The interstellar medium also contains dust, microscopic grains of silicates and carbon, the soot of the cosmos. At normal speeds, this dust is harmless, but we are not talking about normal speeds. To reach the stars in a human lifetime, we need to travel at a significant fraction of the speed of light. At those speeds, a grain of dust hits with the force of a hand grenade. The thin hydrogen gas that fills the void becomes a wall of radiation. As the ship plows through these sparse atoms at relativistic speeds, they strike the hull like a continuous beam of particle radiation, heating the ship and irradiating the crew. The environment is hostile to biology. It is hostile to machines. It is hostile to matter itself. And yet, despite the overwhelming odds, despite the crushing distance and the lethal environment, we have found a reason to go. We have found a destination that calls to us across the 4 light years of darkness. Because out there, floating in the southern sky, is a star system that holds the promise of a future. It is not a yellow sun like ours. It is a small, angry red star, but it is there, and it has a planet. In the next part of this journey, we will look at this destination. We will explore the physics that keeps us trapped here, the tyranny of the speed of light, and the strange relativistic nightmares that await anyone who tries to break the cosmic speed limit. We have left the harbor. The shore is fading. Now we must face the open ocean. Across the gulf of the void, 4¼ light years away, burns a star so dim you cannot see it with the naked eye. If you look up in the southern sky into the constellation of Centaurus, you will see a bright binary pair, Alpha Centauri A and B. They are sun-like stars, swirling in a gravitational dance. But they are not our destination. Drifting a vast distance from them, tethered by a weak gravitational thread, is a third, lonely ember. This is Proxima Centauri. It is a red dwarf, the smallest class of true stars, and it holds the key to humanity's long-term survival. To understand Proxima, you must forget everything you know about our own sun. Our sun is a roaring bonfire, a massive ball of yellow-white plasma that dominates the sky. Proxima is more like a dying candle flickering in a cosmic wind. It is barely larger than Jupiter. If you replaced our sun with Proxima Centauri, high noon on Earth would look like a dim reddish twilight. Plants would die, the oceans would freeze, the sky would turn a permanent bruised purple. It produces so little light that a planet must huddle incredibly close to it, far closer than Mercury orbits our sun, just to receive enough warmth to sustain liquid water. But do not let its small size fool you. This star is a survivor. Our sun is a spendthrift. It burns through its hydrogen fuel at a voracious rate. It has been burning for 4.5 billion years and will die in roughly 5 billion more. When it dies, it will swell into a red giant, swallowing Mercury and Venus and likely scorching Earth into a cinder.
While our sun has a lifespan measured in billions of years, Proxima will burn for trillions. Think about that number. Trillions.
When our sun is a cold, dead white dwarf, when the Milky Way has crashed into the Andromeda galaxy and formed a new, chaotic ellipse, when almost every other light in the universe has flickered out, Proxima Centauri will still be shining. It is the ultimate long-term destination. If humanity wants to outlive the death of stars, if we want to survive until the end of time itself, we must learn to live around red dwarfs. They are the last hearths in a universe that is slowly freezing to death. And Proxima is not alone. Orbiting this dim red bulb is a world, Proxima Centauri b. Discovered in 2016, it is an Earth-sized planet sitting right in the Goldilocks zone, the habitable zone, where temperatures are just right for liquid water to exist on the surface. It is practically next door in cosmic terms. If the galaxy were a city, Proxima b would be the house across the street. But living there would be unlike anything we have ever experienced. Because Proxima b orbits so close to its star, completing a full year in just 11 days, it is likely tidally locked. This means the same side of the planet always faces the star, just as the same side of the moon always faces Earth. On Proxima b, the sun never rises and never sets. One side of the world is trapped in an eternal scorching day, a desert of unending noon. The other side is locked in an eternal freezing night, covered in ice sheets miles thick. Life, if it exists there, would likely cling to the Terminator line, the twilight strip between day and night. Here, in the land of eternal sunset, the temperatures might be mild enough for water to flow. Imagine a civilization living in a world of perpetual dusk, growing black-leaved plants adapted to absorb the weak infrared light of their red sun, fearing the day side as a burning hell and the night side as a frozen abyss. But this world is under siege. Red dwarf stars are unstable. They are prone to violent magnetic tantrums. Proxima Centauri frequently unleashes super flares, blasts of radiation hundreds of times more powerful than anything our sun produces. These flares could strip away the atmosphere of the planet, sterilizing the surface with UV radiation. If there is life on Proxima b, it is likely hiding deep underground or beneath the waves of a dark ocean, protected from the fury of its parent star. So we have a destination, a potential second home, a refuge for the end of time. But between us and this red hope lies the tyranny of distance. And enforcing that tyranny is the strictest law in the universe, the speed of light. To understand why interstellar travel is so hard, we have to talk about Einstein. In 1905, Albert Einstein published his theory of special relativity, and he shattered our understanding of motion. He discovered that the speed of light, denoted by the letter c, is not just a speed, it is a cosmic speed limit. It is the maximum speed at which information, causality, and matter can propagate through the universe. Light travels at approximately 186,000 miles per second, or 671 million miles per hour. It is fast. In human terms, it is instantaneous. If you could travel at the speed of light, you could circle the Earth 7.5 times in a single second. You could reach the moon in 1.3 seconds. You could reach the sun in 8 minutes. But the universe is so vast that even light looks sluggish when you zoom out. Even at this blistering, impossible speed, it takes 4.25 years for light to reach Proxima Centauri. Think about what that means. When you look at Proxima Centauri through a telescope, you are not seeing it as it is now. You are seeing it as it was 4 years ago. If the star exploded today, we wouldn't know about it until 4 years later. We are always looking into the past. And for a physical ship carrying human beings, the situation is much, much worse, because we cannot travel at the speed of light. We cannot even get close. The reason is mass. Einstein's famous equation, E equals mc squared, tells us that energy and mass are interchangeable.
But it also tells us something else. As you push an object faster, as you add kinetic energy to it, that energy effectively adds to its mass. At normal speeds, driving a car, flying a jet, even launching a rocket, this effect is negligible.
But as you approach the speed of light, the effect becomes exponential. To push a spacecraft to 90% of the speed of light requires a massive amount of energy. To push it to 99%, you need even more. To reach 99.9%, you need more energy than our entire civilization produces in a year. To reach 100% of the speed of light, to actually catch the photon, would require infinite energy. It is mathematically impossible for anything with mass to reach light speed. The universe simply says no. It is a hard wall written into the fabric of reality. So let's say we settle for pretty fast. Let's say we build a ship that can travel at 10% of the speed of light. That is 67 million miles per hour. It is thousands of times faster than any bullet, any rocket, any comet. At that speed, you could cross the continental United States in a fraction of a heartbeat. But even at that incredible velocity, the journey to Proxima Centauri would take 43 years. 43 years, an entire career, a marriage, a family, a middle age, and a slide into old age, all spent inside a metal box coasting through the dark. If you left Earth at age 20, you would arrive at age 63. You would spend the prime of your life in the void. And that assumes you can even reach that speed. Currently, our fastest spacecraft, Voyager, travels at a fraction of a percent of light speed. At Voyager speed, the trip takes 73,000 years. We are trying to cross an ocean in a rowboat, and we are talking about building jet skis. But let's imagine we solve the propulsion problem. Let's imagine we build a ship that can travel at 99% of the speed of light. We have mastered fusion or antimatter, and we can scream across the void. Now we run into the second trap of relativity, time dilation. Einstein discovered that space and time are not separate things. They are woven together into a four-dimensional fabric called space-time. And the faster you move through space, the slower you move through time. It is a zero-sum game. If you use all your motion to travel through space, you have none left for time. At 99% of the speed of light, time slows down significantly for the traveler relative to the people staying behind. This is not a mechanical error in the clocks, it is a fundamental property of the universe. Biological processes slow down, atoms vibrate slower, thoughts happen slower. If you traveled to Proxima Centauri and back at 99.9% of the speed of light, the journey might feel like it took only a few weeks or months to you. You would eat a few meals, read a few books, and you would be there. But when you returned to Earth, you would find a nightmare. While only a few months passed for you, nearly 9 years would have passed on Earth. Now, stretch that out to a longer journey. If you traveled to the center of the galaxy, 26,000 light-years away, at 99.99999% the speed of light, you might experience only a few decades of life on the ship. You could survive the trip, but when you arrived, 26,000 years would have passed on Earth. Civilizations would have risen and fallen. The languages you speak would be dead. The people you knew would be dust. You would be a ghost, a relic from a forgotten age, arriving in a future that does not know you. This is the time dilation paradox. High-speed space travel is effectively time travel, but only into the future. It is a one-way ticket. To travel to the stars is to say goodbye to everyone you ever knew. It is to detach yourself from the timeline of human history and drift into a lonely future. This reality forces us to make a choice. We have two options for reaching the stars. Option 1, we accept the slowness. We build massive generation ships that travel at slow speeds, where people live, die, and give birth, passing the mission down to their children and grandchildren, a caravan of humanity inching across the desert. Option 2, we try to break the energy curve. We try to build propulsion systems so violent, so powerful, that they can shove us close to the speed of light, consequences be damned. We try to brute force our way through Einstein's wall. And humanity, being humanity, has already drawn up the blueprints for the brute force method. We looked at the laws of physics, saw the immense energy required, and we turned to the most destructive force we had ever mastered, the atom. In the next part, we will open the classified files of the 1950s. We will look at Project Orion, the spaceship powered by nuclear bombs. We will look at the terrifying engineering of a vessel designed to ride the apocalypse to Saturn. And we will look at its modern successors, ships that harvest the vacuum, ships that sail on laser beams, and ships that carry the power of a star inside them. We have stared at the void, and we have felt the crushing weight of the distances involved. We know the rules. Light is too fast to catch, the stars are too far to reach, and chemical rockets are too weak to matter. To cross the abyss, we need power. Not just a better fuel, but a different state of matter. We need violence. In the late 1950s, a group of brilliant, slightly mad physicists at General Atomics in San Diego came up with a solution. These were men who had worked on the Manhattan Project. They had seen the blinding flash of the atomic bomb, the mushroom clouds rising over the desert, and they looked at that destructive power and thought, what if we could ride it? This was Project Orion. The concept remains the most audacious, brutal, and surprisingly practical spacecraft design in human history. The idea was simple. You build a massive spaceship, something the size of an ocean liner. On the bottom, you attach a gigantic plate of steel, thick and heavy, called the pusher plate. And behind the ship, you eject a nuclear bomb. You detonate the bomb. The explosion creates a sphere of expanding plasma, vaporized bomb casing and tungsten propellant, moving at incredible speeds. This wave of plasma slams into the pusher plate. The plate is coated with grease or oil to protect it from the heat, and it is mounted on shock absorbers the size of skyscrapers. The explosion kicks the ship forward. Then you eject another bomb, and another. Bang, bang, bang. One nuclear detonation every few seconds, pulsating like the heartbeat of an angry god. It sounds like something a child would draw in crayon, put a bomb behind the wagon to make it go fast, but the physics are rock solid. Chemical rockets are limited in the energy in their chemical bonds. Nuclear explosions release millions of times more energy per pound. A single atomic bomb contains enough energy to power a city for weeks. Chain them together, and you have an engine that laughs at the tyranny of the rocket equation. The Orion team calculated that such a ship could reach Saturn in months, not years. It could land on the moons of Jupiter and take off again, fully loaded. And if they pushed the technology to the limit, they calculated they could accelerate a massive arc to about 3 to 5% of the speed of light. That is fast enough to reach Proxima Centauri in about 90 to 130 years. It is slow, yes, but it is doable. It brings the stars within the reach of a single extended human lifetime. Imagine the launch of an Orion starship. It would be the most spectacular and terrifying event in human history. The ship would sit on a launch pad made of solid graphite. As it lifted off, it would leave a trail of nuclear fireballs rising into the atmosphere, a staircase of explosions climbing to orbit. The sky would flash with the light of 1,000 suns. The roar would shatter windows for hundreds of miles. And that was the problem, the fallout. Every launch would pump radioactive isotopes into the Earth's atmosphere, strontium-90, cesium-137. The calculations suggested that a single launch could statistically cause anywhere from 1 to 10 fatal cancers globally due to the fallout. It was a ship that killed people to fly. The project was killed not by physics, but by politics. The Partial Test Ban Treaty of 1963 banned nuclear explosions in space and the atmosphere. Project Orion died on the drawing board, a victim of its own violent nature. It remains the great what-if of space travel, a technology we know would work, sitting on the shelf, waiting for a civilization desperate enough or reckless enough to use it. But the dream of nuclear fire didn't die with Orion, it just evolved. If exploding fission bombs is too dirty, what if we used nuclear fusion? This is the power source of the stars themselves. Instead of splitting heavy atoms like uranium, fission, you smash light atoms like hydrogen together to create helium and pure energy. In the 1970s, the British Interplanetary Society designed Project Daedalus. This was a fusion rocket. It was enormous, larger than the Empire State Building, weighing 54,000 tons. Instead of bombs, it would fire tiny pellets of deuterium and helium-3 into a reaction chamber. Electron beams would zap the pellets, causing them to undergo microfusion explosions 250 times a second.
The exhaust velocity of a fusion rocket is incredible. Daedalus was designed to reach 12% of the speed of light. At that speed, it could reach Barnard's star, its target, about 6 light-years away, in 50 years. It was a true starship. But Daedalus highlighted a new problem: fuel. To get that massive ship moving, 50,000 of its 54,000 tons was just fuel. It was a flying gas tank. This is the curse of rocketry. To go faster, you need more fuel. But adding fuel adds mass, which makes the ship harder to push, so you need more fuel to push the fuel. It is a vicious cycle. So, what if we ditch the fuel? What if we leave the engine at home? We enter the era of the light sail. Deep in the void, there is no wind, but there is light. And light, despite having no mass, has momentum. When a photon bounces off a shiny surface, it imparts a tiny, microscopic kick. It's like throwing a ping-pong ball at a tank. One ball does nothing, but throw a trillion ping-pong balls, and the tank will move. We have already tested this. Japan's Icaros probe unfurled a shiny square sail in space and used the pressure of sunlight to navigate between the planets. It works. But sunlight is weak. It dilutes as you move away from the sun. A solar sail to the stars would be too slow. It would take thousands of years. Enter Breakthrough Starshot. Announced in 2016, backed by physicist Stephen Hawking and billionaire Yuri Milner, this project proposes a radical shift in how we think about space travel. Instead of a massive ship, we think small, microscopic. The plan is to build a star chip, a spacecraft the size of a postage stamp. It would weigh a gram or less. It would carry cameras, navigation sensors, a battery, and a radio transmitter, all etched onto a single silicon wafer. Attached to this chip is a sail, 1 meter wide, made of material incredibly thin and incredibly reflective, thinner than a soap bubble, shiny as a mirror. We launch thousands of these chips into Earth orbit. Then, down on the ground, in a high desert like the Atacama in Chile, we build the beamer. This is a massive array of lasers, kilometers across. We synchronize these lasers to fire a single, coherent beam of light with the power of 100 gigawatts, equivalent to the output of dozens of nuclear power plants combined for just a few minutes. We aim this beam at the sail. When the laser hits, the acceleration is violent. The star chip experiences 60,000 Gs of force. It goes from 0 to 134 million miles per hour, 20% of the speed of light, in just 10 minutes. It is like shooting a bullet at the stars, but the bullet is a smartphone chip. At 20% of the speed of light, the journey to Proxima Centauri takes just 20 years. We could launch them in the 2040s, and they would arrive in the 2060s. The data would take 4 years to beam back, so by the 2070s, we could have high-resolution photos of an alien planet. We could see the continents of Proxima b. We could see clouds, oceans, maybe even the green or black tint of alien vegetation. But there's a catch, a big one. At 20% of the speed of light, you cannot stop. A laser sail has no brakes. The star chips would scream through the Proxima system, crossing the distance from the star to the planet in minutes. They would have a tiny window to snap photos and gather data before they flew past, hurtling into the darkness on the other side, never to return. It is the ultimate flyby, a brief, frantic tourist visit at relativistic speeds. And this technology, while promising, is incredibly difficult. We need materials for the sail that won't vaporize under the laser beam. We need lasers that can focus perfectly over millions of miles. We need a way to receive the tiny, whisper-quiet radio signals sent back by a gram-sized chip 4 light-years away. But notice something. All of these solutions, Orion, Daedalus, Starshot,
are machines. We can imagine sending robust metal plates, hardened fusion reactors, or silicon chips to the stars. Metal can handle radiation. Silicon doesn't get bored. A computer chip doesn't need to breathe, eat, or stay sane. The real problem arises when we want to send us. Biology is weak. We are bags of water and protein, evolved for 1 g of gravity, a thick atmosphere, and a magnetic field to protect us from the sun. In deep space, our bones dissolve, our eyes go blind from fluid shifts, and our DNA is shredded by cosmic rays. If we want to colonize the stars, we cannot just send a chip. We have to send bodies. And since we cannot travel at light speed, we have to solve the problem of time. How do you survive a journey that takes longer than a human lifespan? This leads us to the most haunting concepts in science fiction, which are slowly becoming science fact. We have 3 options for the human cargo. The generation ship, a flying city where you die and your grandchildren finish the mission. Cryosleep, freezing ourselves into a death-like state to cheat time. Transhumanism, changing our bodies or leaving them behind entirely to become data. In the next part, we will board the generation ship. We will explore the sociology of a sealed world. What happens to a society locked in a metal box for 500 years? What happens to the crew forgets why they left? And we will look at the chilling science of suspended animation. Can we really freeze a human being and bring them back? Or is death a one-way street? We have looked at the engines that could scream across the void at relativistic speeds, riding lasers or nuclear fire. But there is a quieter, more somber alternative. What if we accept the distance? What if we accept that the stars are too far for one lifetime? What if we decide to walk? This brings us to the concept of the generation ship. Imagine a city, not a sprawling metropolis, but a dense, high-tech town of perhaps 50,000 people. Now rip that city out of the ground, wrap it in a thick hull of ice and steel to shield it from radiation, and strap an engine to the back. This vessel is not a sprint runner, it is a marathon walker. It travels slowly, perhaps at only 1% or 0.5% of the speed of light. At this speed, the journey to Proxima Centauri takes not decades, but centuries, maybe 1,000 years. The people who step onto this ship at Earth will never see the destination. They will live out their lives in the belly of the machine, maintaining the hydroponic gardens, fixing the recycling systems, and teaching their children the history of a blue planet that is shrinking to a star behind them. These children will grow up, have children of their own, and die. This cycle will repeat for 10, 20, maybe 30 generations. The engineering challenge of a generation ship is staggering, but it is not impossible. We need a closed-loop ecological system. That means absolute recycling. Every molecule of water you drink, every breath of oxygen you take, every gram of waste you produce must be captured, filtered, and reused. A 99% efficient recycling system is not good enough. Over 1,000 years, a 1% loss rate means the ship arrives empty and dead. The ship must be a perfect, self-repairing biological machine. The hull becomes the soil, the air scrubbers become the lungs, the crew become the blood cells. But the engineering is the easy part. Steel and plastic are predictable. The real danger on a generation ship is the cargo, human beings. Sociologists look at the generation ship concept with dread. It is the ultimate pressure cooker. Think about the social dynamic. The first generation, the founders, are volunteers. They're explorers, filled with the zeal of the mission. They chose to leave Earth. But the second generation, they didn't choose this. They were born into a metal prison. They are travelers on a journey they didn't ask for, heading toward a destination they will never see. What happens when the middle generations decide they don't care about Proxima Centauri? What happens when a charismatic leader rises up in year 300 and says, "Why are we sacrificing our lives for the great-great-grandchildren of the founders? Let's turn around. Or worse, let's stop maintaining the engine and just live here." History shows us that cultures drift. Languages change, beliefs mutate. Over 1,000 years, the mission itself might become a myth. The technical manuals might become holy texts, recited but not understood. You might arrive at the destination with a crew who has forgotten how to land the ship. They might look out the viewports at the alien star and feel not hope, but terror, having forgotten that a universe exists outside their hull.
This is the sociological decay problem. A generation ship must be more than a machine. It must be a culture engine, designed to enforce a rigid social structure for a millennium. It requires a society more stable than ancient Egypt and more disciplined than a nuclear submarine maintained for longer than the Roman Empire existed. So, if the human mind is too volatile for the long dark, perhaps we should shut it off. This brings us to option 2, cryosleep. In science fiction, this is easy. The hero climbs into a glass pod, mist sprays, the lid closes, and they wake up fresh as a daisy 100 years later. In reality, freezing a human being is a biological nightmare. We are made of water. When water freezes, it expands and forms jagged, knife-like crystals. If you simply froze a human body, these ice crystals would form inside your cells. They would puncture your cell walls like millions of microscopic daggers. Your blood vessels would burst. Your delicate neural networks, the physical architecture of your memories and personality, would be turned to mush. Upon thawing, you wouldn't wake up, you would simply dissolve into soup. However, nature offers a glimmer of hope. There are animals on Earth that can freeze solid and survive. The wood frog, found in North America, spends the winter as a block of ice. Its heart stops, its brain activity ceases. It is by all medical definitions dead. But when spring comes, it thaws out, its heart kickstarts, and it hops away. How? The frog floods its body with glucose and urea, acting as a natural antifreeze. This prevents the water in its cells from crystallizing into sharp ice. It becomes a syrupy, amorphous solid instead. Scientists are trying to replicate this process for humans. It is called vitrification. The goal is not to freeze you, but to turn you into glass. The procedure would look something like this. You enter the medical bay, surgeons connect you to a machine that drains your blood and replaces it with a cryoprotectant, a high-tech medical-grade antifreeze solution. Then they lower your temperature rapidly. The fluid in your cells doesn't freeze into crystals, it thickens, becoming more and more viscous until it snaps into a solid glass-like state. You are now a statue. Biological time has stopped. You could remain in this state for a year, a century, or a millennium. No aging, no food, no air. But the problem is the wake-up call. We can vitrify small tissues, corneas, heart valves, embryos, and bring them back. We have even vitrified a rabbit kidney and successfully transplanted it back to a rabbit. But a whole human brain? That is a different beast. The brain is incredibly dense and delicate. The cooling process often causes fracturing, cracks in the neural tissue like cracks in an ice cube dropped in water. To revive a cryosleeper, we might need technology that doesn't exist yet. We might need nanotechnology. Imagine waking up not to a doctor, but to a swarm of billions of microscopic robots flowing through your veins. These nanobots would go cell by cell, repairing the fractures, flushing out the toxic antifreeze, and jump-starting your mitochondria. They would have to repair the damage of a century of radiation and thermal stress before you even opened your eyes. And if it works, the psychological horror might be worse than the physical one. Imagine going to sleep tonight. You say goodnight to your family, you see the moon in the sky. You close your eyes. You open them 1 second later, but the lights are different. The air smells sterile. You look out the window and the moon is gone. Earth is a speck of light too faint to see. You are orbiting a red star. You have skipped history. Everyone you ever loved, your spouse, your children, your friends, they didn't just die, they died centuries ago. Their graves are ancient dust. You are a time traveler, stranded in a future that has moved on without you. The culture of Earth might have evolved into something unrecognizable. You are an artifact, a caveman thawed out in Times Square. The isolation would be absolute.
But there's a third option, one that avoids the fragility of the body and the madness of the long wait. What if we don't send the meat at all? What if we send the mind? This is the concept of digital immortality and the von Neumann probe. If you strip away the romance, a human being is an information processing system. Your memories, your personality, your love, your fear, it is all just electrochemical signals firing in a network of neurons. It is software running on wet hardware. What if we could scan that software? This is mind uploading. In theory, if we could map the position of every neuron and synapse in your brain, a connectome, and simulate it in a computer, that simulation would be you. We wouldn't need to send a heavy ship with life support, food, and gravity. We could put your digital soul onto a solid-state hard drive the size of a fingernail. We could put thousands of people on a single chip. We could bolt that chip to a star-shot laser sail and blast it across the void at 20% light speed. The crew would be asleep, paused as data files. When the ship arrives at Proxima Centauri, the onboard computer wakes up. It uses local materials to build robot bodies or grows biological clones in artificial wombs. Then it downloads you into the new body. You go to sleep on Earth, you wake up on Proxima B. You haven't aged a day. But this raises the oldest philosophical question. Is it really you, or is it just a copy? If you upload your mind to the ship and the original you stays on Earth and lives out the rest of your life, which one is real? Are you the person walking on Earth or the data flying to the stars? If the ship crashes, did you die, or was it just a backup failure? While we wrestle with the ethics of copying souls, there is a way to explore the galaxy that doesn't involve humans at all. We could send machines that build machines. In the 1940s, mathematician John von Neumann imagined a machine that could copy itself, a self-replicating probe. You launch one probe to a nearby star. It arrives, finds an asteroid, and sets up a mining operation. It mines iron, silicon, and carbon. It builds a factory, and that factory builds 2 more probes. These 2 probes fly to 2 more stars. They build factories. They build 4 probes, then 8, then 16. It is a viral explosion, an exponential colonization. Even if the probes travel slowly, the math is terrifyingly efficient. Within a few million years, a blink of an eye in cosmic time, these probes would visit every single star in the Milky Way galaxy. Every solar system would have a probe sitting in it, watching, waiting, reporting back. This is the most efficient way to conquer a galaxy. You don't need a massive fleet, you just need one seed, one machine that can replicate. And this leads us to the most chilling thought of all. The universe is 13.8 billion years old. Our solar system is only 4.5 billion years old. There have been billions of years for other civilizations to rise, build von Neumann probes, and seed the galaxy. If it is possible, it should have happened already. The galaxy should be crawling with alien machines. We should see their mining operations, we should hear their radio chatter, we should see Dyson spheres blocking the light of stars. But we see nothing. We look up and the sky is silent. The great silence. This is the Fermi paradox. Where is everybody? Are we the first? Are we the only ones? Or is there something out there, something dangerous that stops civilizations before they can leave their home star? Is there a great filter, a trap that destroys intelligent life before it can leave its home star? Or perhaps the probes are here, waiting, watching, hidden in the asteroid belt or lurking in the Lagrange points, dormant until we reach a certain level of technology. Maybe they're waiting for us to light up the warp drive or detonate the first antimatter bomb. In the next part, we will confront the Fermi paradox. We will look at the scale of alien civilizations, Type 1, Type 2, and Type 3 on the Kardashev scale. We will ask if we are living in a cosmic zoo or a dark forest filled with silent hunters. And we will explore the terrifying possibility that we are alone in a graveyard universe. We have built the ships in our minds. We have designed the engines that ride nuclear fire. and we have imagined the lonely generations living and dying in the void. We have accepted that humanity could colonize the galaxy. The math works, the physics works. Even with slow ships, creeping at a fraction of light speed, a single civilization could populate every habitable star system in the Milky Way in just a few million years. In the 13.8 billion-year history of the universe, a few million years is a blink of an eye. It is a rounding error. So if it is possible, and if the universe is old enough for it to have happened thousands of times over, where is everybody? This simple question, asked by physicist Enrico Fermi over a lunch table in 1950, is the most haunting riddle in science. It is called the Fermi paradox. Look at the numbers. There are roughly 400 billion stars in the Milky Way galaxy. Recent data from the Kepler Space Telescope suggests that up to 20% of those stars have Earth-sized planets in the habitable zone. That means there could be 40 billion potentially habitable worlds in our galaxy alone. 40 billion stages for life to act out its drama. If even a tiny fraction of those worlds developed intelligent life, let's say 1 in a million, there should be 40,000 civilizations out there. Some of them should be millions, maybe billions of years older than us. They should have had ample time to build Dyson spheres, to colonize the galaxy, to send out those von Neumann probes we talked about. Their radio signals should be deafening. Their engineering projects should be visible across the cosmos. But when we point our radio telescopes at the sky, we hear nothing. The cosmic static, the hiss of dying stars, the silence is absolute. To understand how strange this silence is, we need to understand what an advanced civilization might look like. In 1964, Soviet astronomer Nikolai Kardashev created a scale to measure a civilization's power. It is not based on their philosophy or their art, but on energy, the Kardashev scale. Type 1, a planetary civilization. This is a civilization that can harness all the energy falling on its home planet from its parent star. They control the weather, they inhabit the oceans, they can tap into the geothermal heat of the core. They are masters of their own rock. Humanity is not here yet. We are currently a Type 0.7 civilization. We are still burning dead plants, fossil fuels, and squabbling over scraps of land. Physicist Michio Kaku predicts we might reach Type 1 status in a century or two if we don't destroy ourselves first. Type 2, a stellar civilization. This is where things get sci-fi. A Type 2 civilization has outgrown its planet. Their energy needs are so vast that a single world cannot support them. So they go to the source. They harness the entire energy output of their star. How? They build a Dyson sphere. Imagine a shell or a massive swarm of millions of solar satellites completely surrounding a star. They capture every photon, every drop of solar fire, and beam that energy to their habitats or computers. A Type 2 civilization is immortal. Nothing short of a supernova can kill them. They have the energy to terraform planets, to move worlds, to slow down time. To us, they would look like gods. Type 3. A galactic civilization. Now imagine a civilization that has outgrown its star. They spread, they colonize system after system until they harness the energy of the entire galaxy, billions of stars, black holes. A Type 3 civilization would be indistinguishable from nature itself. They could move stars into new orbits. They could tap the energy of the supermassive black hole at the galactic center. They could survive the end of the universe. So if there are 40 billion habitable planets, where are the Type 2s and Type 3s? A Dyson sphere gives off a very specific heat signature, waste infrared heat. We have scanned millions of stars looking for this signature. We haven't found a single one. This silence implies something terrifying. It suggests that there is a barrier, a hurdle in the evolution of life that is incredibly difficult to jump over, a great filter. The great filter is a probability trap. It is a step in the evolutionary ladder that almost no one survives. The crucial question, the question that determines our fate, is this:
Is the great filter behind us or ahead of us?
The filter is behind us. This is the optimistic view. It means that the hard part is already over. Maybe the jump from dead chemistry to the first spark of life, abiogenesis, is incredibly rare. Maybe it only happened once in the galaxy, right here. Or maybe the jump from simple cells to complex animal life is the hurdle. If this is true, then we are special. We are the chosen ones. We are the first generation of the galaxy. The silence is not a graveyard, it is an empty canvas waiting for us to paint. We have a responsibility to fill the universe with life. Or the filter is ahead of us. This is the nightmare. It means that life arises easily. Intelligence arises often. We are not special. But it means that advanced civilizations invariably destroy themselves before they can colonize the stars. Perhaps once a civilization discovers nuclear physics, it always bombs itself back to the Stone Age. Perhaps once they invent artificial intelligence, the AI always decides to eliminate its creators. Perhaps they destroy their planetary biosphere through climate change. If the filter is ahead, then we are walking through a graveyard, unaware that we are next. The silence is the sound of dead civilizations who thought they were the exception. But there are other explanations for the silence, stranger, darker explanations. Consider the dark forest theory, popularized by sci-fi author Cixin Liu. Imagine the universe is a dark forest at night. It is quiet, but it is not quiet because it is empty. It is quiet because it is full of hunters. Every civilization is a hunter with a gun, stalking through the trees. They don't know if the other hunters are friendly or hostile. They don't know if they are weak or strong. So the optimal strategy for survival is silence. If you make a noise, if you broadcast radio signals, if you send out probes, you reveal your location. And in the dark forest, if you are revealed, you are eliminated. Under this theory, the Type 3 civilizations are out there, but they are hiding. They are using stealth technologies. And the reason we haven't heard from them is that we are the only idiots shouting into the darkness. We are the child crying in a forest full of wolves. Or consider the zoo hypothesis. Perhaps the aliens are benevolent. Maybe they have a prime directive like in Star Trek. They know we are here. They're watching us right now, but they have agreed not to interfere. They treat Earth like a nature preserve, a cosmic safari park. Look, they say to their children, there are the humans. Watch them build their little rockets. Watch them fight their little wars. Don't touch the glass. They are waiting for us to mature, waiting for us to stop killing each other, waiting for us to invent a warp drive or solve world hunger. Until then, we are quarantined. Or perhaps the answer is more abstract, the transcendence hypothesis. Maybe advanced civilizations don't expand outward into space. Maybe they expand inward. Once you invent computers powerful enough, why bother with the cold, dead, boring universe of physical matter? Why spend thousands of years traveling to a dead rock like Mars? Instead, you upload your civilization into a virtual reality. You build a computer the size of a planet, power it with a Dyson sphere, and live in a perfect simulated paradise. In a virtual world, you can have infinite magic, infinite pleasure, infinite life. You can manipulate the laws of physics. Maybe the silence is because everyone else has logged on and left the physical universe behind. They are living in the cloud, and we are the only ones still playing in the mud.
Whatever the answer is, the implications are profound. If we are alone, the universe is a vast, fragile place. The entire hopes of consciousness, the only mind capable of appreciating the beauty of the stars, rests on this one small blue marble. If we destroy ourselves, the universe goes back to being blind and dumb forever. We carry the torch of awareness. If we are not alone, then we are the new kids in a very dangerous neighborhood. We are shouting hello into the dark, having no idea what is listening. But let us assume we survive. Let us assume we pass the great filter. Let us assume we dodge the dark forest hunters. We colonize Mars. We reach Proxima Centauri. We build the Dyson spheres. We become the Type 3 gods of the galaxy. What then? There is one final enemy, an enemy that cannot be reasoned with, an enemy that cannot be bombed, an enemy that is built into the very laws of thermodynamics: the end of time. Even the stars must die, even the black holes must evaporate. The universe itself has an expiration date. In the final chapter of our journey, we will look at the heat death of the universe. We will fast forward trillions of years into the future. We will see the era of the black hole farmers. We will see the last light in the cosmos flicker out, and we will ask the ultimate question: can life survive the end of everything? We have traveled from the heliosphere to the red dwarf, from the nuclear pulse to the generation ship, from the silence to the galactic god. Now we face the final curtain. We have reached the final chapter. We have looked at how humanity might leave the cradle, how we might cross the void, and how we might populate the galaxy. We have imagined civilizations that harness the power of stars and reshape the heavens. But even gods are subject to the laws of physics, and the cruelest law of all is the second law of thermodynamics: entropy. It is the tendency of the universe to move from order to disorder, from energy to cold, from life to dust. It is the arrow of time, and it points in only one direction: toward the end. Let us fast forward, not thousands of years or millions, but trillions. The era of starlight, the time we live in now, the time of bright, burning suns and warm planets, will end. It seems permanent to us, but it is just a brief flash in the life of the cosmos. As we move forward in time, star formation will slow down. The great clouds of hydrogen gas that birth new suns will be exhausted. In about 100 trillion years, the last star will be born. It will likely be a small red dwarf sputtering into life in a galaxy that has grown dark and quiet. When that star dies, the lights go out. The universe will enter the degenerate era. The sky will be black. The only objects remaining will be the corpses of stars, white dwarfs, neutron stars, and black holes, and the planets drifting in the dark, frozen tombs orbiting nothing. But life, stubborn, resilient life, might not be dead yet. If our descendants have survived this long, if they have become a Type 3 civilization, they will have anticipated this. They will have changed. They will no longer be biological creatures needing sunlight and water. They will be entities of pure energy or consciousness residing in diamond-hard computer substrates, capable of running on the tiniest trickle of power. In this dark era, the habitable zones will not be around stars, but around black holes. Specifically, rotating black holes. A spinning black hole drags space around with it, creating a region called the ergosphere. Physicist Roger Penrose theorized that a civilization could dump waste into the black hole and, through a trick of gravity, extract energy from its rotation. This is called the Penrose process. Imagine cities built on ring worlds orbiting a supermassive black hole. They don't look up in a sun, they look down at the singularity, harvesting its spin to power their thoughts. They would be black hole farmers, huddled around the last campfires in the universe.
Because computer processing becomes more efficient at colder temperatures, these future minds could think faster and deeper than we ever could. They might run simulations of entire universes inside their servers. To them, a second might feel like a billion years. They could live subjective eternities in the dying dark. But even black holes are not immortal. Stephen Hawking discovered that black holes radiate energy, Hawking radiation. They slowly evaporate. Over timescales that defy comprehension, years expressed as a 1 followed by 100 zeros, the black holes will shrink and explode. When the last black hole evaporates, we enter the black hole era, and finally, the dark era. At this point, the universe is a soup of photons and subatomic particles stretched thin by the relentless expansion of space. The temperature is absolute zero. No energy flows, no work can be done.
Nothing changes. The universe has reached maximum entropy. This is the heat death, the big freeze. It is the ultimate deadline, the final full stop of the story of existence. Or is it? Theoretical physics offers a few desperate glimmerings of hope. Some theories suggest that the universe is cyclical, that the heat death is not the end, but the prelude to a new Big Bang, a big bounce. Others suggest the multiverse, that our universe is just one bubble in an endless foam of realities, and that advanced life might find a way to tunnel out of this dying bubble and into a young, fresh one. But we don't know. As far as we know today, this is it. We have one shot, one universe, one timeline. This realization, the finiteness of existence, changes the meaning of our journey. If the universe is going to die, if everything we build will eventually turn to dust, why bother? Why struggle to reach Mars? Why suffer the centuries in a generation ship? Why build the Dyson sphere? Why leave the cave at all? Because we are the universe's way of knowing itself. Without life, without consciousness, the universe is just a play with no audience. It is a vast, beautiful, violent mechanism that exists for no one. A nebula is not beautiful if there are no eyes to see it. A supernova is not tragic if there are no minds to mourn it. We give the universe meaning. We are the custodians of meaning. By spreading to the stars, we are not just saving our DNA, we are saving the memory of the universe. We are ensuring that the story continues as long as possible. We are fighting a war against the dark, a war that we will ultimately lose, but a war that is noble because it is fought at all. Every rocket launch is an act of defiance. Every child looking through a telescope is a rebel against the void. Every probe we send past the heliopause is a declaration that we were here, that we mattered, that we tried. Right now, Voyager 1 is still out there. It is cold, it is alone, its nuclear heart is fading. In a few years, it will stop speaking to us, but it will keep flying. It will fly long after your great-grandchildren are dead. It will fly long after the sun swells and consumes the earth. It will fly until the stars burn out. It carries a gold record that says this is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. It is up to us to make that record not a tombstone, but a prologue. The ocean is vast, the water is cold, the distance is terrifying, but we have built the ships, we have drawn the maps. The shore is fading behind us.
We have looked at how humanity might leave the cradle, how we might cross the void, and how we might populate the galaxy. We have imagined civilizations that harness the power of stars and reshape the heavens, but even gods are subject to the laws of physics. And the cruelest law of all is the second law of thermodynamics, entropy. It is the tendency of the universe to move from order to disorder, from energy to cold, from life to dust. It is the arrow of time, and it points in only one direction, toward the end. Let us fast forward, not thousands of years or millions, but trillions. The era of starlight, the time we live in now, the time of bright burning suns and warm planets, will end. It seems permanent to us, but it is just a brief flash in the life of the cosmos. As we move forward in time, star formation will slow down. The great clouds of hydrogen gas that birth new suns will be exhausted. In about 100 trillion years, the last star will be born. It will likely be a small red dwarf, sputtering into life in a galaxy that has grown dark and quiet. When that star dies, the lights go out. The universe will enter the degenerate era. The sky will be black. The only objects remaining will be the corpses of stars, white dwarfs, neutron stars, and black holes, and the planets drifting in the dark, frozen tombs orbiting nothing. But life,
stubborn, resilient life might not be dead yet. If our descendants have survived this long, if they have become a Type 3 civilization, they will have anticipated this. They will have changed. They will no longer be biological creatures needing sunlight and water. They will be entities of pure energy or consciousness residing in diamond-hard computer substrates capable of running on the tiniest trickle of power. In this dark era, the habitable zones will not be around stars, but around black holes, specifically rotating black holes. A spinning black hole drags space around with it, creating a region called the ergosphere. Physicist Roger Penrose theorized that a civilization could dump waste into the black hole and, through a trick of gravity, extract energy from its rotation. This is called the Penrose process. Imagine cities built on ring worlds orbiting a supermassive black hole. They don't look up at a sun, they look down at the singularity, harvesting its spin to power their thoughts. They would be black hole farmers, huddled around the last campfires in the universe. Because computer processing becomes more efficient at colder temperatures, these future minds could think faster and deeper than we ever could. They could run simulations of entire universes inside their servers. To them, a second might feel like 1 billion years. They could live subjective eternities in the dying dark. But even black holes are not immortal. Stephen Hawking discovered that black holes radiate energy, a phenomenon known as Hawking radiation. They slowly evaporate, over timescales that defy comprehension, years expressed as a 1 followed by 100 zeros. The black holes will shrink and explode. When the last black hole evaporates, we enter the dark era. At this point, the universe is a soup of photons and subatomic particles stretched thin by the relentless expansion of space. The temperature is absolute zero. No energy flows. No work can be done. Nothing changes. The universe has reached maximum entropy. This is the heat death, the big freeze. It is the ultimate deadline, the final full stop of the story of existence. Or is it? Theoretical physics offers a few desperate glimmerings of hope. Some theories suggest that the universe is cyclical, that the heat death is not the end, but the prelude to a new Big Bang, a big bounce. Others suggest the multiverse, that our universe is just one bubble in an endless foam of realities, and that advanced life might find a way to tunnel out of this dying bubble and into a young, fresh one. But we don't know. As far as we know today, this is it. We have one shot, one universe, one timeline. This realization, the finiteness of existence, changes the meaning of our journey. If the universe is going to die, if everything we build will eventually turn to dust, why bother? Why struggle to reach Mars? Why suffer the centuries in a generation ship? Why build the Dyson sphere? Why leave the cave at all?
Because we are the universe's way of knowing itself. Without life, without consciousness, the universe is just a play with no audience. It is a vast, beautiful, violent mechanism that exists for no one. A nebula is not beautiful if there are no eyes to see it. A supernova is not tragic if there are no minds to mourn it. We give the universe meaning. We are the custodians of meaning. By spreading to the stars, we are not just saving our DNA, we are saving the memory of the universe. We are ensuring that the story continues for as long as possible. We are fighting a war against the dark, a war we will ultimately lose, but a war that is noble because it is fought at all. Every rocket launch is an act of defiance. Every child looking through a telescope is a rebel against the void. Every probe we send past the heliopause is a declaration that we were here, that we mattered, that we tried. Right now, Voyager 1 is still out there. It is cold, it is alone, its nuclear heart is fading. In a few years, it will stop speaking to us, but it will keep flying. It will fly long after your great-grandchildren are dead.
It will fly long after the sun swells and consumes the earth. It will fly until the stars burn out. It carries a gold record that says, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings." It is up to us to make sure that record is not a tombstone, but a prologue. The ocean is vast, the water is cold, the distance is terrifying, but we have built the ships, we have drawn the maps. The shore is fading behind us. It is time to set sail.